on, if you have a stationary AR process, AR1 process, you know that if you have a stationary AR1 process, you can always write this is a stationary AR1 process. Yeah? We have seen that if the value of phi is less than 1, absolute value of phi is less than 1, this process can be written as alpha upon 1 minus phi plus Et plus phi Et minus 1 plus phi square Et minus 2 phi cube Et minus 3 plus phi raised to 4 Et minus plus phi raised to j Et minus j and so on. Sure? You can write this. We have seen that so far, right? By the recursive substitution formula. And then taking the limit as j tends to infinity, this becomes alpha upon 1 minus phi plus. Now what is this? This is indeed saying that yt actually is a constant plus a phi shock plus last period shock into a constant plus the shock 2 periods back into a constant and so on. Infinitely many. So this is really an MA process of infinite order. So every stationary AR1 process is in fact an MA process of infinite order. Right? This is nothing but really an MA infinity process because we are writing yt as a constant plus a sum of infinitely many past shocks. The beauty is because the value of phi is less than 1, these quantities keep on becoming smaller and smaller and smaller, so finite sum is possible. Right, so the important thing is every stationary AR process can be written as an infinite order MA process. Every stationary AR process can be written as an infinite order MA process. Okay, now let's look at an MA process carefully. Okay, let's look at an MA process carefully. What is an MA process? Think of yt is equal to Et plus theta Et minus 1, right? Okay, yt is equal to Et plus theta Et minus 1 MA1 process. Like we can write an AR1 process as an infinite order MA process, can I write an MA1 process as an infinite order AR process? Can we invert the question? We saw that a stationary AR1 process can be written as an infinite order MA process. If an AR process is stationary, I can write it as an infinite order MA process. So what is the condition that an MA1 process will have to satisfy in order to be able to, in order to be writable as an infinite order AR process? Is the question clear? Okay. So let's do something smart. Here I have Et is equal to yt minus theta Et minus 1. Right? I can write it like this. Everybody agrees? Just sort of interchanging? Right. But if this is Et, it means that I must have Et minus 1 as yt minus 1 minus theta Et minus 2.
Yeah.
Right? So I must have yt minus 1 minus theta Et minus 2. Right? You see the point? Okay? Which is what? Which is equal to, which says, so Et is equal to yt minus theta yt minus 1 plus theta square Et minus 2. Right? Which can be written as yt minus theta yt minus 1, okay, yt minus theta yt minus 1 plus theta square, what will this be? Yt minus 2 minus theta Et minus 3, right? Yt minus 2 minus theta Et minus 3. Okay, this is what? This is yt minus theta yt minus 1 plus theta square Et minus 2, right? Okay, sorry, so which can be written as, this becomes yt minus theta yt minus 1 plus theta square yt minus 2 minus theta cube Et minus 3. Sure? Which is E. Okay? Or, if you think of this a little bit smartly, I can now rewrite this as yt is equal to et plus theta yt minus 1, okay? Now I am taking everything on this side. Et plus theta yt minus 1 minus theta square yt minus 2, right? And if I actually put here, you will see that I will actually be able to write this as right? I can write this continuously like this. I can keep on doing that, no? Because this can be substituted again and so on and so on. Right? So here, but when does this make sense? This makes sense only if the value of theta is less than 1. Because the value of theta is less than 1 only when the powers of theta become smaller and smaller and smaller. And I can write yt as et plus the past value of yt into constant plus another value into yt into another constant and so on. Only if the values of those thetas keep on becoming smaller. If the value of theta is equal to 1 or the value of theta is greater than 1, then theta raised to 4 is bigger than theta raised to 3 and so on. So a finite sum will not exist. So for yt to be able to, so for us to be able to write, so if you have an MA1 process, yt is equal to theta et minus 1 plus et. If you want to write this MA1 process as an infinite order AR process, the value of theta has to be less than 1 in absolute terms. You see the point? Which is called invertibility. Right? Stationary process, if you want to write it as an infinite order moving average process, and MA1 process has to be invertible if you want to write it as an infinite order AR process. If you want to write it as an infinite order AR process. You want to write it as an infinite order AR process. Is this clear? Sure? Everybody gets this very important point. So for AR processes, there is a condition stationarity. You want to write it as infinite order MA processes. For an MA1 process or in general for MA processes, if you want to be able to write them as infinite order AR processes, the corresponding condition is invertibility. All MA processes are necessarily stationary, but not all are invertible unless theta is equal to 1. Now why is this important? This is important for understanding general processes which are AR as well as MA, which are called ARMA processes. Which are very important forecasting tools. Okay, fine. Therefore, the stationarity and invertibility ideas are relevant there, right? Okay. Before that, we'll just explore the properties of an MA process a little bit more carefully. Okay. Think of an MA1 process. Is the idea of stationarity invertibility clear? Okay. So think of an MA1 process. Okay. We found two things. We found three things. Expectation yt is equal to 0. Right? We found and we found expectation yt minus 1 is equal to theta sigma square e. Okay. Can you tell me what would be expectation yt minus 2? We call this gamma 1 or usual. What will be gamma 2? Can you tell me what would be gamma 2? It will be expectation yt minus 2, right? Which will be what? expectation of Et plus theta Et minus 1. What will be Yt minus 2? Et minus 2 theta Et minus 3. Right. So into. Now if you multiply these terms, do you get any common terms? No. This will be Et minus 2, Et minus 3, Et minus 1, Et minus 2, Et minus 1, Et minus 3. So there will be all the expected values will be 0 because all those are uncorrelated. So we get gamma 2 is equal to 0. So if you have an MA1 process, only gamma 1 will be non-zero and subsequently all the other gammas will be 0. Similarly, you can try out if you have an MA2 process, only gamma 1 and gamma 2 will be non-zero, all the other gammas will be 0. If you have an MA7 process, only gamma 1, gamma 2, gamma 3, gamma 4, gamma 5, gamma 6, gamma 7 will be non-zero, others will all be 0. Right? So how does an MA process differ from an AR process? An MA process, so there are two things, okay, fine. So if you look at the autocovariance functions, now something very important. Consider the autocovariance function of an AR1 process and an MA1 process. The autocovariance function of an AR1 process will be infinitely long-lived but keep on becoming smaller and smaller and smaller. Right? The autocovariance function of an MA1 process will only have non-zero values at lag 1 and then be 0 throughout. Only gamma 1 will be there, gamma 2, gamma 3, gamma 4 will all be 0. Right? So in general, if you have an ARP process, the autocovariance functions at order P, right? Autocovariance functions will keep on becoming smaller and smaller and smaller, right? For an MAQ process, the first Q autocovariances will be non-zero, others will be 0. Is this clear to everybody? Sure? So that's an important difference between the autocovariance functions of an AR process and an MA process. If you have an AR3 process, the autocovariance function will still be tapering off slowly, infinitely long-lived. If you have an MA3 process, only gamma 1, gamma 2, gamma 3 will be non-zero, others will be 0. On the other hand, think of the partial autocorrelation function of a stationary and invertible AR and MA process. So think of a stationary AR process, right? It's an AR3 process. The partial autocorrelations will exist only at lag 1, lag 2, lag 3 because there are only 3 direct correlations, right? There are only 3 direct correlations, so the partial autocorrelation will exist only at lag 1, lag 2, lag 3. What do you think will be the partial autocorrelation function of an MA3 process, which is invertible? If you have an invertible MA3 process, what do you think will the partial autocorrelation functions look like? For example, take the example of the invertible MA1 process which I wrote, and then we could write that as an infinitely long-lived AR process. We could write this as Yt is equal to Et plus 5 Yt minus 1 minus 5 square Yt minus 2 plus 5 cube Yt minus 3 minus 5 raised to 4 Yt minus 4 and so on. So here Yt was now directly correlated with lag 1, lag 2, lag 3, lag 4, lag 5, lag 7 and infinitely many such lags. So Yt will in fact have infinitely many partial autocorrelations, but the 5's will keep on 5 squares, 5 cube, 5 raised to 7 will keep on becoming smaller and smaller and smaller. So if you have an invertible MA process, so if you have an invertible MA3 process for example, it will have 3 autocovariances which are non-zero and the partial auto